Are you afraid your next late-night alert could spiral into a full-blown outage? On this Tuesday at 3:14 a.m., a PagerDuty notification signaled high latency on a customer-facing API gateway. The on-call engineer logged in, expecting a minor issue, but found customer transactions timing out. Application logs showed a flood of connection errors. Systems were grinding to a halt. Initial checks revealed nothing obvious. Servers online, CPU normal, network stable. Digging deeper, the engineer noticed the memory usage for a core microservice was steadily climbing. A classic memory leak. The process wasn't crashing, just consuming RAM until the system hit severe memory pressure. The kernel began swapping pages to disk, causing disk I/O wait times to skyrocket. This I/O contention was the root cause of the API latency. The fix, a rolling restart of the offending microservice, which immediately restored performance. Crisis averted, but the real work began, understanding how a simple memory leak cascaded into a major outage. This story is all too familiar for systems engineers. It highlights a critical truth-robust process, and memory management is essential for reliability. Without proactive monitoring and a deep understanding of Linux resource management, these costly fire drills will repeat. The goal isn't just faster fixes, but building systems where such incidents are rare. Mastering these concepts transforms reactive admins into proactive engineers. Every incident is a lesson in building more resilient infrastructure. Poor memory management is a hidden tax on your business. Downtime during outages means lost transactions and revenue, sometimes thousands per minute. The damage to brand reputation and customer trust can be even greater. But costs go beyond outages. Chronic memory pressure slows applications, degrades user experience, and forces over-provisioning of expensive hardware. Engineers are pulled into late-night firefights, burning out your best talent and stifling innovation. High turnover and constant recruiting add to the expense. Each quick fix and server restart adds technical debt, making systems more fragile. Over time, this fragility slows feature delivery and reduces business agility. The true cost combines downtime, wasted resources, burnout, and lost opportunities. Mastering memory management isn't just technical, it's a business imperative. Invest in it to protect your bottom line and future growth. To manage processes, you must understand their life cycle in the Linux kernel. Processes transition through states: running, R, interruptible sleep, S, uninterruptible sleep, D, and zombie, Z. R means executing or waiting for CPU, S is waiting for an event like I/O. D state signals a process stuck waiting on I/O, often a sign of storage issues. Zombies are terminated children whose parents haven't collected their exit status, leading to process table leaks. Too many zombies or D-state processes can freeze a system. The Linux scheduler balances CPU and I/O needs, ensuring fairness. Recognizing these states helps you diagnose issues. A process stuck in D is different from one maxing out CPU and R. Each state points to a distinct class of problem. Understanding the lifecycle is key to effective troubleshooting. And are just the beginning for process monitoring. Advanced tools like BCC, BPF compiler collection, leverage eBPF for deep, low-overhead kernel insights. Use Memleak to trace memory allocations in real time and pinpoint leaks. BioLatency reveals block I/O delays, helping diagnose storage bottlenecks. The Perf tool profiles CPU usage, showing which functions consume the most cycles. PerfTop and Perf Record Report provide real-time and historical performance analysis. The /proc file system offers detailed kernel metrics. ProcMeminfo for memory, /proc/slabinfo for kernel allocations. Combining BCC, Perf, and /proc gives a multi-dimensional view of system health. These tools move you from symptom chasing to root cause analysis. Master them to diagnose and resolve issues with precision. Diagnosing issues is only half the battle. Prevention is key. Systemed, C groups, and U limits form the backbone of proactive process control. Systemed unit files let you set resource limits like memory max and CPU quota per service. These settings translate to C group configurations, isolating and protecting critical workloads. Groups partition resources, CPU, memory, I/O among process groups, preventing one app from starving others. U limits set per user or per process caps like open files or process count, guarding against predictable failures. Raising file descriptor limits for databases or web servers can prevent outages. Layering systemed C groups and U limits creates a robust defense against resource exhaustion. This approach keeps systems stable, even when individual apps misbehave. Proactive controls are your first line of defense. Beyond limits, you can guide the Linux scheduler to prioritize what matters most. Use Nice to set CPU priority, lower values for critical apps, higher for background jobs. A simple Nice adjustment can keep user-facing services responsive during heavy load. Ionis manages I/O priority, set backups or batch jobs to idle so they don't compete with databases. This prevents non-essential I/O from impacting critical services. CPU affinity via TaskSet binds processes to specific cores, improving cache efficiency and isolating workloads. Dedicate cores to high-performance apps, and relegate others to separate cores for predictable performance. These tools let you fine-tune resource allocation, reducing jitter and contention. Intelligent scheduling ensures critical services always get what they need. Use Nice, Ionic, and CPU affinity together for optimal system performance. Prioritization is as important as limitation. The final step is automation, creating a flywheel of monitor, alert, remediate, and learn. Use tools like Prometheus and eBPF agents to collect detailed metrics. Set intelligent alerts, predict memory exhaustion before it happens, not after. When alerts fire, trigger automated runbooks. Capture diagnostics, restart services, or adjust priorities. Automation handles incidents quickly, reducing downtime and manual toil. Feed incident data back into the system for continuous improvement. Postmortems drive permanent fixes and smarter automation. Each cycle strengthens your defenses and reduces future risk. The automation flywheel frees engineers to focus on innovation, not firefighting.